All right, how's it going? How's homework? Not bad.
It was hard, but it made a lot more sense this time.
Okay.
Yeah, for sure.
Good.
I mean, I understand it. Except for 8.
Questions about homework before you turn it in. What's up with 8? Is that the multiplexer? That's the up-down counter. Yeah, so these are funky circuits for question 8. So this is the solid version of it. Let's see what's going on here. So we have a binary up counter. That's like the 7493. Okay, it's something with a clock, and the clock is drawn like this. So the triangle tells you this is edge triggered. Okay, it's just a symbol. It means it's a clock. It's going to respond to an edge. Positive edge or negative edge? Positive edge, right? If there's no bubble over here, this is responding to the positive edge. If there's a bubble, it means it's the negative edge. Okay, it's going to clock when the clock ticks from 1 to a 0. That's when the action happens. So this is a positive edge triggered up binary counter. How many bits? 4, okay. So the outputs are generally labeled Q, A, B, C, D, that's 4 bits. So it's a 4-bit up counter. So what's the highest number it counts to? More than that.
8 or 9?
More than that.
16.
Ignoring the circuit.
15.
What was the last one?
15.
15, all right, we got it. So it will count up to binary, this value, okay, which is 1 plus 2 plus 4 plus 8. So that's 15. So it counts from 0 to 15, so a total of 16 different possible values. All right, and this counter has what's called a synchronous load input. So it says up here, clear bar and load are synchronous inputs. So synchronous means that what you do on these inputs has no bearing on anything until the clock ticks. Okay, the clear line is a clear signal. It's got a bubble on the front, so if I put a 0 into this clear, it's supposed to clear the counter. But because it's a synchronous clear, grounding out that pin does not immediately clear the counter. It says the next time the clock ticks, clear the counter. Okay, clear doesn't come into play here because clear is pulled up to power. So it's never driven low, so there's no clear operation going on. But the load input is interesting because it's connected to QD, which is an output. So when the load input is high, right, there's no bubble on the load signal, so it's active high. So when a 1 goes into that load line, on the next clock tick, whatever values you have over here in A, B, C, D, those get loaded into the internal memory of this counter. And they basically become the current value for QA, QB, QC, QD. So if you wanted to preset this thing to a 5, you could set up your inputs to be 1, 0, 1, 0. That's binary 5. And then the next time the clock ticks, doesn't matter what the current count is, instead of just counting up 1 more, it'll change the count to be equal to 5. Okay, that's what a preset or a load input does. So with all of that in mind, what is this circuit doing? So let's suppose that it starts off at 0. There's no reason it would start at 0. Let's just suppose it starts at 0. So we're going to make a table. Q, A, B, C, D. And let's suppose they're all 0. So what's going to happen when the clock ticks? Positive edge. What's going to change here? So QD is the most significant bit, QA is the least significant. The current count is 0. When the clock ticks, it's going to count up by 1, which is going to change the value to this. So yes, QA is the only thing that changes. And the next time the clock ticks, it's going to count up again to the value 2. And then 3, and so on. But the next tick might be more interesting. So in all of these cases so far, QD is 0, which means if we trace that line around and we come up over here, this load input is 0. So it's not doing anything, right? The load has no effect yet. But the next time the clock ticks, our counter, because it's a counter, is going to count from 7 to 8. And after that clock tick, now QD is going to be a 1. And since QD goes into that load input, now the load input's equal to 1. But this happens right after the clock tick, right? The clock tick occurs, and what takes place? The counter changes from 7 to 8. Okay, when that clock tick occurred, the load input was still 0. So it has no effect yet. But now that the clock has ticked and our output is 1, 0, 0, 0, there's a 1 sitting on that load input. And it's not going to do anything right now, but the next time the clock ticks, it's going to look at the load line and say, hey, there's a 1 on the load input. I should do something different. So what's it going to do when you tick the clock and there's a 1 on the load input?
Put A, B, C, and D to Q, A, B, C.
It's going to put A, B, C, and D into QA, QB, QC, QD. Okay, it's going to load these inputs over here, and it's going to basically set the counter's count to match these 4 inputs. So what are A and B equal to?
1.
Those are 1s because they're tied up to VCC, and C and D are tied to ground, so those are 0s. So the next clock tick, these are going to become 1s, these are going to become 0s. And in particular, since QD is a 0, now that load input is 0 again. So what happens on the next clock tick? It just counts up. And one more tick, it counts up to 8, and then on the next clock tick, we just did this. It's going to go back to 0, 0, 1, 1.
So you can set A, B, C, and D to whatever you want to
Mhm.
get it to load and switch to the thing where you want it to restart.
Mhm.
Yeah, okay.
Yeah. So in this case, it's going to count 3, 4, 5, 6, 7, 8, and it's just going to go back to 3 and keep repeating this pattern.
So if D was to the VCC, it would just reload itself continuously?
Good question. So if D was tied to VCC, it would load in the value 1, 0, 1, 1. And then on the next clock tick, that load input would still be 1, so it would load 1, 0, 1, 1 again, and it would basically not count anymore. It would just keep loading at one fixed value, and that would be all it does for the rest of its life. And I think that gets you a bit into what the unsolved question was asking also. So does this analysis sort of make sense? Right, it's a really strange circuit because we don't usually take outputs and just tie them into inputs like this, but we could, and we can analyze it, right, just by sort of breaking down what it's doing at each piece. So the way that this answers the question, it just shows 3, 4, 5, 6, 7, 8, and then back to 3. But there's also the fact that if you happen to start with a 0 in the counter, you'll count 0, 1, 2 until you get into this pattern. If you happen to start with a value like 12 in this counter, so where these were 0, 0, 1, 1, the next clock tick will immediately take you to state 3, right? Because that load line will be 1. So the unsolved question 8 used similar looking diagram, but different specifics. Okay, QD is still going to the load line, but here in this case, we have what you just asked. D is tied to VCC. And so it asks you for a state diagram for the circuit. What's the mod of this counter? We'll talk about that in a sec. Is this counter useful? Okay, and the answer we found is probably no, because it stops counting pretty quickly. So change one value to make a mod 9 counter. Okay, what do we mean by mod 9? A mod 9 counter, a mod n counter counts basically from 0 to n minus 1. So mod n counter. Counts up to n minus 1 and then goes back to 0. So a total of n different values, but since the first one is 0, the last one's n minus 1. So a mod 9 counter, we would want to go 0, 1, 2, up to 7, 8, and then back to 0, 1, 2, and so on. So with that in mind and with that analysis that you've done, how can we change these presets to make this a mod 9 counter? So sort of a trial and error analysis kind of exercise. How'd you do with question 9? So we said we'd talk about this today.
Can't say what we're, I don't, I'm not 100% sure how I do.
So let's look at timing issues. So suppose we're building a state machine and we're using flip-flops, and your flip-flops have a setup time of 10 nanoseconds and a hold time of 5 nanoseconds. All right, so this is setup, and this is hold. If those are the only timing constraints that we have to worry about, well, we have a picture in an earlier problem of a flip-flop timing diagram. So here's the clock which is driving your flip-flop, and EI, that's your excitation input. So that's the input going into the flip-flop. If it's a D flip-flop, it's the D input. If it's a JK, it's the J and K inputs, right? What we're trying to capture in this is that this line where number 1 appears, this dotted line, That's the negative edge of the clock, okay? This is a negative edged flip-flop. That's where the clock tick occurs. This gray area before the clock tick, that's the setup time. And it says the excitation input cannot change anywhere in this gray area. It's got to be stable at least this far before the clock tick. Okay, it could be stable longer than that, that's fine. But once we hit this gray area, we're getting close to where the clock's going to tick, we're not allowed to change the inputs. Okay, the width of this gray area, that's the setup time. And after the clock tick, we're not allowed to change anything until a certain amount of time has passed. That's the hold time. So if we mimic that, so let's draw, let's see, I did a 10 nanosecond setup time. We're going to do a 5 nanosecond hold time, so just a little bit after. Did I switch clock edges on you? I did. Okay, I forget this one. All right, so these are the bands during which nothing is allowed to change. And this is clearly 15 nanoseconds, 10 plus 5. So if these are the only time constraints on the system, what's the fastest clock that we could possibly have that doesn't violate this idea that nothing can change inside here? It's really just 15 nanoseconds. We could do something like this. Right, so the clock ticks, we have to wait the required hold time, that's 5 nanoseconds. And at that point, assuming that our inputs are now changed immediately to whatever they need to be, right, we still have to wait another 10 nanoseconds before the clock can tick. So clock ticks, we've got to wait 5 seconds for hold time. And then we could instantaneously change all the flip-flop inputs, and then we have to hold them there for another 10 nanoseconds, and then we're clear to do another clock tick. So the absolute fastest we could tick would be 1 tick every 15 nanoseconds. And that's assuming that after the clock ticks and after the hold time has passed, right, we can immediately come in and set up our new inputs and say now we're in our 10-second hold time.
So if there's such a small gap for the time to like pick up like an input while the clock is ticking, wouldn't there be like a lot of discrepancies?
Yeah, this is an absolutely idealized maximum clock speed.
Like, I mean, every time like the computer would accidentally put it into the time setup or whatever, wouldn't that cause a bunch of errors and stuff like that? Or would it just kind of ignore it until the clock ticks?
It will ignore it until the clock ticks. But in this case, we're saying that once you're within 10 nanoseconds of the clock tick, everything's got to be in its final value. You're not allowed to make any changes. Right? That's the idea of the setup time.
Handle that?
a practical computer? No, in reality, we're going to need some space in between here and here. So let's draw a practical circuit and see if this answers the confusion. Because this is idealized, right? We're just looking at an absolute maximum, but let's look at a practical state machine. We've got a memory. We've got logic. And the output of the logic feeds the input of the memory. And we've got some other stuff. We've got outputs and we've got inputs and so on. So let's just look at this little feedback loop. Flip-flops, logic, goes back in, feeds the inputs of the flip-flops. So this logic has some propagation delay, right? Once you change some of the inputs into here, those changes will go through gates and they'll go into inverters and they'll go through other gates, and all those steps have propagation delay. And the time from your input to output we can call tau sub p. Okay, that's propagation delay. So now let's look at the timing on the system. Suppose the setup time is 10, these are all nanoseconds. The hold time is 5, and let's say the propagation delay is 40. So worst case, there's a combination where when you change these inputs, you gotta wait 40 seconds before the outputs are correct. Okay, and these are always worst case figures, because you gotta plan for the worst case. It may be you change an input and nothing changes, right? Technically your outputs are valid immediately. Okay, but we can't bank on that. So worst case, let's say 40 nanoseconds from input to output. So let's look at what the timing of the system looks like now. So here's a clock tick. We've got 5 nanoseconds of hold time during which we're not allowed to change the inputs to the flip-flop. But we also have 40 nanoseconds of propagation delay. And after that propagation delay has passed, the outputs that are going into the flip-flop inputs are stable. So now we can start counting off our setup time. And after that setup time has passed, we can have another clock tick. So here's the only slightly weird thing to note about this. The hold time is usually a lot smaller than the propagation time. Right? The time we're required to keep these inputs stable in the memory, the hold time, is usually a few nanoseconds. And this complex logic is usually going to take more than a few nanoseconds before any of its outputs start changing. Right? If you have one inverter in here and you change the input, it's going to be 4 or 5 nanoseconds before the output responds. So usually this hold time gets absorbed inside this propagation delay. And so the overall minimum time between your clock ticks is probably your propagation delay plus your setup time. So in our case, that's 50 nanoseconds. So we can tick every 50 nanoseconds. That's 20 megahertz. And that's the fastest we can run this state machine. Right, so right, just take reciprocals to go from period to frequency. So if you can tick every 50 nanoseconds, that's 1 over 50 times 10 to the minus 9th. And that'll be 20 times 10 to the 6th, 20 meg. So we can do this kind of analysis on our state machines if we know setup time of the flip-flops, hold time, which usually doesn't factor in, and then propagation delay for the logic circuit. And it's basically how quickly can your outputs here go through your logic, come back around, and then be stable here to satisfy the setup time. As soon as that much time has passed, you can tick the clock. And now you have to wait for that propagation delay. These come around, wait for the setup time. After that, you can tick the clock again. You can tick it slower, you can tick it once a day, it's gonna work fine, but the fastest you could do would be, in this case, 50 nanoseconds.
What causes different gates that have longer, shorter propagation delay?
Interesting question. There's different ways to build gates. There's different technologies. So we're using a technology called CMOS in the chips that you have in your parts bins. You could buy chips using something called TTL. It's a different kind of technology. Functionally, they work exactly the same. Right? An AND gate is an AND gate. They even have the same pin numbering in most cases. They take 5 volts. But what they're doing internally can be very different. And different technologies operate at different speeds. So emitter coupled logic, ECL, was really, really fast. Okay, it worked really, really quickly, but it was really power hungry. If you build a whole computer out of ECL, you needed a little generator next to it to supply power, right? Because it just consumes so much juice. And there's different kinds of chips that you can get. You can get a CMOS inverter that's very inexpensive and has a propagation delay of a few nanoseconds. You could probably buy one that's very expensive and has a delay in picoseconds. If you need that, you'll spend the money and you'll get a chip that's made with different technology or maybe smaller devices or operates at a lower voltage or something.
Is it just better materials or better design? Or
Well, better is a little subjective, right?
Right.
Because if it costs 10 times as much, maybe it's not better to you, right? But yeah, it's differences in materials, it's differences in design. The way that you actually put the transistors together to implement something can be different. So we work with CMOS, but there's an older version of technology which was called NMOS, right? Took a little more power and it was also slower, but it was easier to build. The manufacturing that you needed to build an NMOS circuit was not as complex, right? But it wasn't as fast, and it took more power. So when we got up to millions, tens of millions of transistors, that little bit of extra power for NMOS became a big deal breaker, and everything switched to CMOS eventually. It can also change. I mean, if you go into your parts bin and you pull out 5 inverter chips and you measure the propagation delay, you're going to see different numbers. It's just physical characteristics, imperfections in the manufacturing, time of day, temperature in the room, all kinds of things can affect it. So on the data sheets, you always get a worst case for these kinds of things. The setup time is the worst case setup time. Probably it'll work with a smaller setup time, but it's not guaranteed. Okay, this is why overclocking works. I don't know what's going on over there. This is why overclocking works sometimes, because there's usually an extra band that things will still work in, and you just explore that space.
Back to the homework on number 7. It becomes a SR FF type, and one of the characteristics of that is that when it's 1-1 for the SR, it's illegal. And on the table, when it tells us to do the table for number 7,
Yeah.
there is a legal state a couple times.
Yeah, so some people asked me about this, and my suggestion was look in the book and see what it lists for 1-1. It's not illegal in the sense that your chip will explode, okay? It's illegal in the sense that we think of S equals 1 as saying set, R equals 1 as reset. If they're both 1, we're asking the chip to both set and reset, and that's nonsensical. So the chip will be either set dominant or reset dominant, and I think it's reset dominant in the book, which means that particular input wins out. Okay, so yeah, so if they're both 1, it puts it to a 0.
Gotcha.
In practice, we don't use SRs, right, just because there's this weird extra state, and we get everything we need with JK. All right, other homework questions? Yeah.
On question 7, what on the flip flops on the outputs of Q naught, what is that little circle?
This one down here?
Yeah.
Oh, I wouldn't put that there, but if this, yeah, so this would normally be labeled Q bar, and it would just have a line coming out, and you just understand that it's the complement of whatever's coming out of Q. A possibly different way to show that is with this little bubble here, which means this is the complemented output. But I think it's somewhat ambiguous, right?
So it's just Q bar?
So it's just Q bar. In this case, it's Y1 bar. So it's labeled Y1, you know, they use the quote instead of the bar. So that tells you this is the inverse of Y1. This is the inverse of Y2. But the symbology here, I would usually put Q with a bar on top. And I think that's what you see more often. But there's a lot of kind of casualness in the symbology. For example, up here is an inverter, but it's shown with a bubble on the input, right? Well, it is an inverter, right? Because this right? What is this? Well, this is just something that takes an input and it passes it to the output. It's like a wire, okay? And this is like the same thing, but with an inverter on the output. And that's what we know of as an inverter. But if we think of this as just something that takes the output and sets it equal to the input, then this is the same thing, but the input's getting inverted, so this is actually y equals x bar. And you might even see something like this. And this would just be y equals x. And there's no sane reason why you would put something like that in your picture, but you'll see them sometimes. And the key is to not get too upset. There's notions of we're very biased usually in 250 and in most of our engineering. We think of 1 as like the action state. 1 is on. 1 is when the LED is lit, right? 1 is when there's a voltage coming out of here. And we think of 0 as like off, quiescent, low, inactive, right? But that kind of leads us to bias where we have an input labeled go, and we assume everybody believes that that means if we put a 1 into the go input, the chip's gonna go, right? But we could flip that totally on its head and work in what's called negative logic, where we think 0 is the action state. And when we have an input labeled go, obviously what we mean is put a 0 in there if you want it to go. And it's no more right or wrong than what we normally do, where we think of 1 as the action state. But if you flip everything on its head like that, you get a very consistent view of the world. And a lot of these bubbles that we see are related to this idea of having negative logic, right? So it gets semi-political / religious if you go too deep into it. So if there's things like that that are unclear, definitely ask, including if it's on a test or something, right? Because symbology is not always perfectly defined in this stuff. Yeah.
So I think Y2 bar inverted is just Y2 there.
You mean here?
Yeah.
Yeah, that's why I don't like having the bubbles and the labels that say bar. No, this line is just Y2 bar.
It's just Y2 bar. It's not.
It's not another copy of
Double
Y2.
negative?
It's the complement. Yeah, there's no double negative here, even though that's technically what it says, right? And this really bothered me when I started reading these things, because to me that's a double negative.
Yeah.
But no, it's telling you the same thing 2 different ways, which is what you do when you say there's no way I'm going to do something. You're trying to emphasize it, right? That's what they're doing here.
That's another problem.
Yeah.
Gotcha.
All right, so go ahead and pass in your homework, and let's see what you got.
Oh, I got it. This is just,
Okay, cool. All right, anybody else? Cool. All right. So I don't know at this point how the calendar looks for the labs, but let's not panic about the labs, okay? I think it may be that the next lab is due like a week from Tuesday or something.
Yeah.
So I'm hoping that by Tuesday we'll be able to talk about it, but if we aren't, then we'll push it back however much we have to push it back, okay? So we're not gonna be concerned with that too much. The next lab is going to be a software lab. Okay, it's something you're going to do using a computer program called Icarus Verilog. And we're going to be talking about Verilog next week. It's a language for defining circuits. And then the lab will be basically some exercises that you'll use Icarus for to design some circuits and simulate them and write up a lab report on it and such. So it won't be something that you're doing where you're putting things into proto boards. Okay, in fact, we're done with those labs completely because lab 8 will be a different kind of lab and it's optional. But before we get there, right, we want to talk about the other side of what we've been doing. So what we've been doing so far is analyzing state machines. Okay, so we're given a circuit, which is a state machine. And we define some states. And then which gives us like a state assignment table. And then we write equations for flip-flop inputs. And then, I don't have my cheat sheet with me. I posted the cheat sheet on Canvas, or the reference sheet for state machine analysis. So write equations for flip-flop inputs, and the system outputs. And then you make a state transition table. And then we make a state diagram. And then we're done. So that's what we've been doing. We start with a circuit, we basically analyze it, and we work towards a state diagram, which tells us how the system behaves, right? And once we have the state diagram, we might actually do some other analysis, figure out what it all means. And then we're done. So we look at the state diagram and we say, okay, so this thing is a counter. And if this input X is 1, it counts up, and if it's 0, it counts down. And if input Y is 0, it stops counting, and if it's 1, it keeps counting. And it counts from 2 to 5, and then it goes back to 2. Right, so we start with a circuit diagram, we end up with this understanding of what the circuit's behavior is. Okay, so that's the analysis. So the flip side of that is synthesis. And we just run this in the other direction. Right, we basically start with what our circuit is supposed to do. We're trying to build something that counts in a certain way or moves from this state to that state under these conditions. And from that, we're going to draw a state diagram And then once we have a state diagram, we're going to basically make a transition table. And once we have a transition table, we'll come up with equations for flip-flop inputs. And once we have the equations for flip-flop inputs, we can use that to draw a circuit. So we're really going to do the same steps, we're just going to kind of run them in a different direction. But along the way, these things are going to probably feel somewhat familiar. Okay, which is a good thing. So let's just start with an example of a machine, and then we'll take a break, and then we'll start getting into the mechanics of how we do this. So what sort of machine should we do? Let's do the mood machine. Okay, so this is a machine that's going to predict what your mood is. Okay. And this will pop up in a future lab. So you have 4 moods. You have very happy, you have happy, you have sad, and you have very sad. And here's our key. And we have one input to this system, which is W. Okay, so what is W? 1 means that it's sunny, 0 means it's cloudy. And the weather's the same all day. Can't be partially sunny. So here's how this machine defines your mood for tomorrow. The clock tick is the sunrise, okay? So if you're very happy and it's sunny today, you're going to be very happy tomorrow. So this is a sun lover centric example. If you're very happy today but it's cloudy all day, your mood's going to go down a little bit. Next clock tick, which is when the sun rises and your alarm goes off, you're going to be happy but not very happy. And if you're happy but it's cloudy again today, tomorrow you're going to be sad. And if it's cloudy that day, the next day you're going to be very sad. And if it's cloudy when you're very sad, you're going to be very sad the next day too. But if you're very sad and the sun's out all day, next day you're going to be still sad but not quite as sad. And if the sun's out that day, then you're going to wake up, you're going to be happy. And if you get 3 days of sunshine in a row, wow, you're going to be very happy. So that's our mood predictor. Okay? And it's basically a machine. You feed it one binary input, which is, was it sunny today or was it cloudy today? And tick the clock and it will tell you what your mood's going to be tomorrow. Right? Or maybe this is what's really inside our brains, I don't know. Okay? So it's an example, but it's actually a real world example from computer science. There's a little version of this inside your CPUs on your smartphones and your laptops. And this does something that is very real and computer science-y. So we'll talk about that later. All right, so let's take a 5-minute break, and then let's see how we can go from this to an actual circuit that implements this behavior.